is there a reason to use a concurrent flow heat exchanger if the countercurrent is always more efficient? And I would say we are going to look at a case where it won't matter. And that's a case where we have a constant temperature on one side of this system. So the last case to consider would be, what if, and that's a great question, because it segues very nicely. What if this is steam, and so THI and THO are just T steam and T steam? If it's atmospheric pressure, it's 100 degrees Celsius. It comes in at 100 degrees Celsius as a saturated vapor, and it leaves at 100 degrees Celsius as a saturated liquid. And so if there's no delta to speak of here, we'll call it TH or TS, then this won't make a difference. If I have the cold fluid coming in here, or if I have the cold fluid coming in the other side, it is absolutely symmetric. So if I have phase change, steam, we'll look at the math at why this is true. But now, I don't necessarily care if I'm counterflow or coflow. Excellent question, Patrick. Yep. This is a case where it won't matter. And this is common for you to use steam and to use phase change materials and to have a constant temperature on one side of these heat exchangers, and then you don't care anymore. And we'll look at the reason why. Excuse me. Good question. Lost the page here. All right, so this is the general situation we have. I think as a young engineer, trying to get a grasp of shell and tube heat exchangers is not very easy. The thing that really is confounding with these systems is thinking about I have my cold fluid coming in. We'll have it come in on the left. If I'm warming up a cold single-phase liquid, and I know that I have it starting at some cold temperature and leaving at some hot temperature, and I put a macroscopic control volume around this tube, it's going to tell me that the heat I've added to this cold liquid, by the time it's made at this certain delta X, is going to be M Cp delta T. Where I'm looking at this just in the context of thermodynamics. I don't care anything about this. All I know is I have a certain amount of liquid that's gone from a low enthalpy to a high enthalpy. If it's an incompressible liquid, then I know delta V is 0, PdV is 0, and my entire heat transfer is MCP delta T. This is going from left to right. Like I said, if I have a shell around this thing, and now let's set this up as our old inefficient heat exchanger where we have, not orange one, the inlet temperature, hot temperature over here, and the outlet hot temperature over here. The other thing that we need to think about isn't the overall increase of temperature and change of enthalpy of one phase as it's entering and exiting the heat exchanger. But the idea that we would like to get a sense of Q from the hot stream to the cold stream. And this is what gets confounding, is thinking about, all right, so I'm doing these balances where I have Q as MCP delta T. If this is also a liquid that's starting at some hot temperature and it's cooling down, then that's also MCP delta T. And these are equal because thermodynamically speaking, in the context of equilibrium, whatever heat I remove from one fluid had better equal the heat that I've added to the other fluid if this system is well insulated and I don't allow for heat to escape and go anywhere else. These two things better be equal. Of course, we'll have a different specific heat and mass flow rate, but it's true that those have to be equal.